to 3 minus. A horizontal line is generated to classify plus and minus based on higher weight of the misclassified observation. In the final step, D1, D2, and D3 are combined to form a strong prediction that has complex rules as compared to the individual weak learners. AdaBoost algorithm and flowchart. Now, since you know the workflow of AdaBoost classifier, let's understand the AdaBoost algorithm. A weak classifier is prepared on the training data using the weighted samples. Only binary classification problems are supported, so every decision stump makes one decision on one input variable and outputs a plus 1.0 or minus 1.0 value for the first or second class value. The misclassification rate is calculated as error equals correct minus n divided by n. In the given equation, error is the misclassification rate. Correct is the number of training instances predicted by the model, and n is the total number of training instances. So let's understand the steps involved in this algorithm. Step 1, initially data points is weighted equally with weight. Wi equals 1 over n, where n is the number of samples. Step 2, a classifier H1 picked up that classifies the data with minimal error rate. Step 3, the weighted factor alpha is dependent on errors ET. Step 4, weight after time t is given as this formula, where z is the normalizing factor, H1x, yx is the sign of the current output. Let's understand the flow of AdaBoost algorithm. It follows the following steps. 1. Initially, AdaBoost selects a training subset randomly. 2. It iteratively trains the AdaBoost machine learning model by selecting the training set based on the accurate prediction of the last training. 3. It assigns the higher weight to wrongly classified observations so that in the next iteration, these observations will get a high probability for classification. 4. Also, it assigns weight to the trained classifier in each iteration according to the accuracy of the classifier. The more accurate classifier will get higher weight. 5. This process iterates until the complete training data fits without any error or until it reaches the specified maximum number of estimators. Gradient boosting. Now let's understand gradient boosting. Gradient boosting trains several models in a very gradual, additive, and sequential manner. The major difference between AdaBoost and a gradient boosting algorithm is how the two algorithms identify the shortcomings of weak learners, that is, decision trees. GBM minimizes the loss function, MSE, of a model by adding weak learners using a gradient descent procedure. Gradient boosting involves 3 elements. 1. A loss function to be optimized. 2. A weak learner to make predictions. 3. An additive model to add weak learners to minimize the loss function. Let's understand the GBM mechanism. Gradient boosting trains many models sequentially. Each new model gradually minimizes the loss function of the whole system using the gradient descent method. So in y equals ax plus b plus e, e needs special attention because it is an error term. The learning procedure consecutively fits new models to produce an additional accurate estimate of the response variable. The principal idea behind this algorithm is to construct new base learners that might be maximally correlated with negative gradient of the loss function associated with the whole ensemble. So let's understand the working gradient boosting. GBM predicts the residuals or errors of the prior models and then sums them to make the final prediction. Step 2, one weak learner is added at a time, and existing weak learners in the model are left unchanged. Step 3, GBM repetitively leverages the patterns in residuals and strengthens a model with weak predictions. Step 4, modeling is stopped when they do not have any pattern that can be modeled. Let's look at the steps involved in GBM algorithm. Step 1, Fit a simple regression or classification model. Step 2, calculate error residuals, that is, actual value minus predicted value. Step 3, fit a new model on error residuals as target variable with the same input variables. Step 4, add the predicted residuals to the previous predictions. Step 5, fit another model on residuals and repeat steps 2 and 5 until the model is overfit or the sum of the residuals become constant. XGBoost. Let's understand extreme gradient boosting. It is a library for developing quick and superior gradient boosting tree models. XGBoost is one of the implementations of the gradient boosting concept, but what makes it unique is that it uses a more regularized model formulation to control overfitting, which gives it better performance. Thus, it helps to reduce overfitting. Extreme gradient boosting is a custom tree-based algorithm used for classification, regression, and ranking with custom loss function. It has interfaces for Python and R that can be executed on Yarn. XGBoost is extensively used in ML competitions as it is almost 10 times faster than other gradient boosting techniques. Let's understand the XGBoost library features. XGBoost library tools are built for the sole purpose of model performance and computational speed. Let's look at system features followed by algorithm features. We will finally take a look at the model features of XGBoost. System features are parallelization. Parallelization. It produces tree construction using all CPU cores while training. Distributed computing. It uses a cluster of machines in order to train very large models. Cache optimization. Data structure involved in XGBoost makes the best use of hardware. Algorithm features are sparse aware. Algorithm behind XGBoost provides automatic handling of missing data values. Block structure. It supports the parallelization of tree construction. Continued training. Its algorithm provides continued training in order to boost an already fitted model on new data. Model features are gradient boosting. It uses gradient boosting machine algorithm, including learning rate. Stochastic gradient boosting. It does subsampling at the row, column, and column per split levels. Regularized gradient boosting. It does regularization using both L1 and L2 regularization.